this is again a very broad topic, but for this course, we'll make a very brief introduction. Okay, so Earth is obviously got a very nice balmy average of a global mean of 15 degree centigrade, which is considered very important for life because, as we know, we have water in liquid form, in water vapor form, and frozen as snow and ice, glaciers and so on. And obviously atmosphere compared to the radius of the earth, which is some 6371 kilometer, the atmosphere and ocean are just a few kilometers, so they are easily treated as shells, thin shells, for all purposes, for computing circulations, weather, climate, and so on and so forth. There is various ways in which the atmosphere sustains life. The most important one being the water cycle. Evaporation puts the water into the atmosphere. It condenses from clouds, transported in the atmosphere far distances, rains and snows in places where there is no evaporation because warm latitudes are supplying the moisture all the way, and so on. And the greenhouse effect, the blanket that the earth has because of these gases, like water vapor, carbon dioxide, ozone, methane, nitrous oxide, and so on, they regulate sunlight, right? The atmosphere is obviously dominated by oxygen, which is almost 21%, nitrogen, which is almost 78%. So only tiny bit of trace amounts of these other gases are present. Ozone, as many of you probably know, is very important in the stratosphere because it absorbs UV and forms oxygen, forms ozone. UV is not good for life and DNA, so it doesn't come in heavy amounts into the troposphere, the lower atmosphere where we live. But when ozone is formed from various industrial activities and burning of fossil fuels in the cars and so on, it is a pollutant. It causes greenhouse gas warming, which we will see, and it is not good for health either. So atmosphere regulates sunlight, and it obviously regulates climate also, especially when we include the ocean, which has a huge heat capacity compared to atmosphere. So you can think of a pot of water on a stove. The stove is got fire that you can see, like the sunlight. It's in the visible. The pot gets hot. It warms pretty fast because its heat capacity is low, but you cannot see how hot it is because it's emitting in infrared radiation. The water inside heats much slower because its heat capacity is much larger. That's kind of what happens on Earth, right? The sun's radiation is coming in visible bands so we can see it. Everything is heated by the sun's energy, and energy is going out as thermal or infrared and near infrared, kind of like the emission from our skin, which you cannot see, but you can obviously feel the heat, right? That's the brief introduction. So this is kind of what we can think of. Greenhouse effect is kind of reminds you of the greenhouse in which you grow things, where sunlight comes in and the heat getting out is retarded or slowed down. But actually the blanket is a better analogy. Sun's incoming radiation is, let's say, 100%. About 30% of it is directly reflected by various bright surfaces. So that's called albedo. So Earth's net albedo is about 30%. So 30% of the energy coming in as sun's energy is directly lost to space. The remaining 70% or so is moved around. It goes into evaporating the water, heating the land, melting ice, and so on, and has to go back out as infrared radiation for energy balance. What greenhouse warming essentially is like putting a blanket where you trap your own body heat. So they allow the incoming radiation to come in, and their molecules, specifically triatomic molecules like carbon dioxide, nitrous oxide. Methane is of course got 4 atoms, but H2O. They have a mode of vibration or bending and rotation which is excited by the outgoing infrared photons of radiation. So they trap the energy, in the sense they get warmer and they send the energy back to Earth. That's what creates global warming. Okay, the example to look at is the distance of the planets from the Sun. So there is Venus, there is Earth, and here is Mars. Venus is only receiving 165 watts per meter squared because it's full of clouds. It's completely covered in clouds. So almost 75% of the 659 watts per meter squared it receives is reflected back. And yet it reaches a temperature of 462 degrees centigrade on the surface because its greenhouse effect is so powerful that it's taking this little energy and creating what is called a runaway warming. Obviously we have to worry about it because we are receiving only 341 watts per meter squared. We are reflecting only 30% of it, and we are keeping 242 watts per meter squared and creating a temperature of 15 degrees centigrade. But if we keep increasing the greenhouse effect by increasing greenhouse gases, how warm can we get? Can we get as warm as Venus? There is no evidence because in Earth's history we never got that warm, but the question is how warm can it get and whether we can survive the full extent of warming. Mars receives much lower amounts of energy, has a much lower albedo, and hence its temperature is also much lower. Okay, so that's how you understand the so-called Goldilocks syndrome. The Goldilocks porridge needed temperatures that were not too hot, not too cold, and just perfect, right? So Earth in some ways right now has a perfect energy balance as far as we know to allow life in the current form, but obviously we keep reading exciting news that there is water and ice in the solar system, on moon of the Earth, and also on the moons of Saturn and Jupiter and so on. And the general idea is that wherever there is water, there is likely to be some form of life. Obviously, we haven't found evidence yet, but indirect evidence has been found even on Venus, where certain chemicals that are only produced by biotic reactions are found in the atmosphere. That's how satellites look for evidence of life. Are there any chemicals that are produced on Earth purely by biotic activities and not inorganic activities, abiotic activities? If you find evidence, then you guess that maybe there is life on that planet. It's very likely in the coming decades we'll find some evidence, considering how much water and ice is there in the solar system. So in the meantime, let's get back to Earth and see what will happen to Earth if we keep creating more and more global warming, stronger and stronger global warming.